All right, so let's get started. This is the first mini lecture for the first week of class. As I told you guys in class when we went over the course, we're going to chunk these lectures up into mini lectures. So there's going to be 4 mini lectures for this first section here on water. And I'll also apologize for my voice. As I'm recording these lectures, I'm coming off of a bit of a cold, so that'll hopefully resolve itself as the semester wears on. So we're talking about Chapter 2 from the textbook today. This is water, obviously something that all of you are familiar with already, and a lot of what we review in these first few lectures are going to be things that you've heard in other classes. We try to start at a place where you're comfortable and already have some prior knowledge, and we'll build off of that. As we go through these chunked lectures, we'll cover polarity as a chemical property and how polarity influences water, and we'll just talk about that in this first chunk here. In the later versions of this lecture and the chunks that you'll see in the next 3 parts, we'll also talk about why water is considered the universal solvent, the idea of hydrophilic versus hydrophobic interactions and properties, hydrogen bonds, van der Waals, and other non-covalent interactions that occur, and we'll talk about acids, bases, pH buffers, and we'll even talk quite a bit about pKa. But in this first mini lecture here, we'll only talk about polarity. So water is a polar molecule. And what we mean by that is that water has 2 different ends. It's important that we go down this road because this planet is a watery planet. Life evolved in a watery environment, and all of us are literally bags of water. You can think of terrestrial organisms as bags of water where the balloon of that bag of water is our skin, and everything that's inside of us is floating in a watery environment. It's no surprise, because you've learned it in other courses, that it's widely believed and understood that life evolved in the oceans first. Life began in water. And so the chemistry of life also evolved to work best in that watery environment. Eventually, after life got complex and it was able to climb out of the oceans and become terrestrial, it wasn't wise to evolve an entirely new terrestrial way of existing biochemically. So instead, when life crawled out of the oceans, it took the ocean with it. All of the biochemistry that was occurring in the water now occurred inside of us. We are essentially bags of salty seawater. So as we go through this semester and we go through these lectures, you'll see just how important water is. It plays a critical role in biochemistry throughout all of the reactions that we're going to be discussing. And so in order to understand how water influences all of that chemistry, we have to understand water itself as its own molecule. And that's what we'll be doing here. So again, water is a polar molecule. It has 2 different ends. Well, let's give that a little bit more meat. What we really mean by 2 different ends is that we have 2 different charges. Water as a molecule has an unequal charge distribution. If we were to say that more simply, we would say that one side of water is a little bit positively charged, and the other side of water is a little bit negatively charged. So we can use this as an example. This isn't water, this is an amino acid, but we can use this as an example of what I'm saying. But wait a minute, there's a problem with this example, because I said that water is a bit negatively charged on one side and a bit positively charged on the other. And here you can see full charges. This is a full positive charge and a full negative charge. So how can anything be a bit charged? What does that really mean? And we get to these partial charges through a chemical property called electronegativity. So water is a perfect example of electronegativity in action. Here's water, a very classical depiction of water, where we have a single oxygen molecule and coming off of it 2 covalent bonds, 1 to 2 different hydrogens. So we have H2, 1, 2 hydrogens, H2O, O for oxygen. So when we say electronegative, we mean fundamental properties of some atoms. Oxygen is a highly electronegative atom, so too is nitrogen, but we're talking about water here, so we'll talk about oxygen first. And when an atom is electronegative, it has a strong affinity for electrons. In other words, electronegative atoms like oxygen exert strong attractive forces onto electrons that they are near. So the electrons that are in the covalent bond between hydrogen and oxygen, and remember what we mean by that, this covalent bond that's indicated here is actually a shared pair of electrons. Those shared electrons zoom around hydrogen, and they zoom around oxygen, and they zoom around hydrogen, and they zoom around oxygen. And because those electrons are making those figure 8 orbitals, they hold these 2 atoms very close together. That's the covalent bond. And there's another pair of electrons doing the same over here. Those electrons zoom around hydrogen and zoom around oxygen, making those figure eights and keeping this hydrogen close to oxygen as well. So we have these shared electrons that are making up these covalent bonds between oxygen and hydrogen. And because oxygen is electronegative, it's exerting a strong attractive force on those electrons. So we can think of oxygen as an electron magnet. Oxygen draws electrons towards it. If oxygen is acting as a magnet for electrons, and those electrons are constantly zooming around these hydrogens and oxygens, which of these atoms do you think those electrons will be drawn to more? And if you thought or said oxygen, you're right. Since oxygen is electronegative and oxygen has this magnetic property for electrons, those electrons are going to be spending more time and drawn more highly towards oxygen. So those electrons are being pulled towards oxygen, the electrons of the covalent bond. Remember that electrons are negatively charged, so if electrons are negatively charged and they're spending more time around oxygen, what do you think the charge around oxygen might be? And if you said negative, you're correct. But here's where that bit part comes in. It's not a full negative charge around oxygen because oxygen doesn't always hold those electrons near it. Those electrons are zooming around oxygen and zooming around hydrogen. So as they zoom around oxygen, those electrons slow down because they like being around oxygen. And then as they whip around hydrogen, they do so very quickly so they can get back to oxygen and slow down. And then they zoom around hydrogen very quickly. Because those electrons aren't always around oxygen, that negative charge is not full. But because those electrons are around oxygen more than they're around hydrogen, oxygen does have that negative charge. That's a partial negative charge, and that's symbolized by this lowercase delta. So anytime you see this baby delta, this lowercase delta symbol that I'm indicating here, with a negative charge next to it, that means partial negative or partly negative. Now, back to those examples of those zooming electrons. If those electrons are zooming around hydrogen and oxygen, and they're zooming around hydrogen quickly, and they're lagging when they're near oxygen, and we have a partial negative charge around oxygen, what do you think the charge around hydrogen might be? Remember, hydrogen is electron deprived. Those electrons are racing around hydrogen as quickly as they can so they can get back to oxygen where they want to be. And the answer there is a partial positive charge. Both of the hydrogens of oxygen have a partial positive charge because they're electron deprived. The electrons are spending far less time around hydrogen, and because the electrons are negatively charged, negative charge is spending far less time around hydrogen, making that hydrogen more positive than it would normally be. And this is why water is a polar molecule. It's polar because it has two different ends. It's polar because it has an uneven charge distribution. It's polar because one end of oxygen, one end of water, the oxygen end of water, has a partial negative charge. Electrons are remaining around that oxygen more often. The other end of water has a partial positive charge. The negatively charged electrons are spending far less time around those hydrogens, making them partially positively charged. As I mentioned, nitrogen is also highly electronegative, so when nitrogen is involved in bonds with hydrogen, the same thing happens. The more those electrons spend time around nitrogen, nitrogen takes on a partial negative charge, and the oxygens that nitrogen is bound to remain partially positive. Now I'd like you to imagine this. Imagine another water molecule, identical to this one, floats by, and that water molecule is oriented in the way that I've shown here on this slide. Remember, it's another identical water molecule, so we have a partial negative charge around that oxygen. And now if you look, we have a partial negative charge from this oxygen and a partial positive charge from this hydrogen, and opposites attract. So now we have a partial electrostatic interaction between something that's mildly positive and mildly negative. Because of that attraction, we have a non-covalent bond. Now, many of you know of or have taken classes with my wife, and so this idea of opposites attracting probably won't strike you as that foreign of a principle. If you know Dr. QM and you know me, you have all the proof you need that opposites attract. But it's also true here of these partial positively and partial negatively charges. This interaction that I'm showing here, this is a hydrogen bond or an H bond. A hydrogen bond is a non-covalent bond between an electronegative, partially negative atom and a partially positive hydrogen on another molecule. Said another way, a hydrogen bond is a weak, again non-covalent, interaction or bond between a partially positive hydrogen on a H-bond donor molecule and a partially negative electronegative atom, such as oxygen or nitrogen, on a H-bond recipient or receiver molecule. H-bonds are responsible for many of the properties that we see in life. Enzymes function and are held together into their three-dimensional shape because of hydrogen bonds. And if you've taken cell and molecular biology with me, or even genetics with me or somewhere else, you know that it's hydrogen bonds that keep bases paired in the two strands of DNA. DNA is double-stranded because of hydrogen bonds interacting between base pairs. It's important to have the counterpoint here, which is that not all molecules are polar, of course. Not all molecules behave in this way. Not all molecules have partial charges or are capable of engaging hydrogen bonds. We also have nonpolar molecules. So here's an example of a nonpolar molecule. This is carbon dioxide. There's no polarity here. There's no uneven charge distribution. There are no partial charges across a carbon dioxide molecule. And so this is a nonpolar molecule. This doesn't have any partial positive or partial negative charges. It doesn't have any full charges, so it doesn't interact with anything in the way that we just described with water. These nonpolar molecules, they have no charge characteristics or no charge chemistry of any kind. The textbook that we use in this course shows this diagram to show water. This is a very, very busy diagram. We see bond angles, van der Waals radii, covalent bonds, but what we want to pay special attention to is the baby deltas. Here we have a lowercase delta positive, meaning this hydrogen has a partial positive charge. And we have a lowercase delta negative here, indicating that this oxygen has a partial negative charge. This face of this water molecule is partially positive, and this face of this water molecule is partially negative. So every water molecule has two hydrogens, which can each engage in single H bonds each. They are single H bond donors. And the oxygen can actually accept two H bonds from another molecule. So we have four possible H bonds that a water molecule can make. If we look at that another way, here the solid lines are covalent bonds, and the dotted lines are hydrogen bonds. Here is the water molecule we're interested in. And we see that this one hydrogen, because it's partially positive, can make an H bond or a hydrogen bond with something else like water. The partial positive here interacts favorably with the partial negative here. This hydrogen, also part of that same water molecule, can do the same and make a single hydrogen bond with something else that's partially negative. The oxygen of this water molecule is partially negative. It can accept two hydrogen bonds from two different water molecules. 1, 2. And so this one water molecule that we're considering here is capable of making 1, 2, 3, 4 total hydrogen bonds. And indeed, that's what happens in ice. That's why ice has a crystalline pattern, because water makes 4 hydrogen bonds when it engages in ice as a solid form. So, taken at its crux, what we're saying here is that water really likes to stick to water. Water has a high affinity for other water molecules. Water has partial negative charges that can interact with the partial positive charges of other water molecules. And those interactions add up over how many water molecules are being involved. There's strength in those numbers. So we have lots and lots and lots of hydrogen bonds that are possible with water. Each hydrogen bond is fairly weak and non-covalent, but we have lots and lots of them. And so the analogy I always like to use for this example is Velcro. The single interaction within Velcro, one tiny little plastic hook engaged with one hair width little plastic loop, is a severely weak interaction. If you ever want to see this, and you're very, very bored and have plenty of time on your hands, get a magnifying glass and hook a plastic hook of Velcro to a loop of Velcro on the other sheet. Try to do just one, and look to see how easy it is to pull those two apart. Conversely, if you are to fully engage the soft side of Velcro with the rough side of Velcro, That's a very difficult Velcro interaction to pull apart. You get a very large whoosh as you pull those apart from one another. And that's because lots and lots and lots of weak interactions come together to make a strong interaction in total. Water molecules work exactly the same way. Water sticks to water very well in large numbers because all of those individual very weak H-bonds, like those individual weak hook-loop interactions of Velcro, come together in large numbers and make for a very strong affinity or interaction. When water is in its liquid form, it's constantly exchanging partners for its H-bonds. It's almost like a line dancing endeavor where water makes an H-bond with another water molecule and then rapidly breaks it and makes another H-bond with another water molecule, almost as though they're do-si-doing or dancing arm in arm, trading partners as the song goes on. But again, because so many H-bonds are engaged at any one time, there is a lot of strength in liquid water, of water sticking to water. And this results in a very interesting biochemical property about water, and that is that it is liquid. If a chemist from another planet were to land on this planet, and you were to show that alien chemist the structure of water, that alien, he, she, it, would tell you that water is a gas. Here are two gases we're familiar with. Ammonia is NH3, whereas water is OH2, and methane, CH4. The molecular weight of ammonia is about 17 Daltons. Of methane, it's about 16. The melting points are well below zero, and the boiling points are below zero as well. What that means is that ammonia and methane boil well below zero. So at room temperature, it's completely boiled off. It's a gas. Here's water, OH2 or H2O. Its molecular weight is 18. It should have similar melting points and boiling points as ammonia and methane. Well below zero, water should boil and become a gas, and all the water we observe should be a vapor or gas. But we know that's not true. We know that the metric system is actually based on water. The zero of the metric units of the centigrade system is zero because that's where water freezes into solid. And water doesn't boil until you hit 100 degrees centigrade, which is quite high, very scalding. Why? The reason why water is a liquid and not a gas like ammonia or methane, its two close cousins, is because of H-bonds. Water having an affinity for other water molecules, water sticking to water, makes it that more difficult to separate individual water molecules and make them a gas. When water is with water, it holds on tight, and it doesn't want to let go. And if you want to break those bonds, you have to put far more heat. In fact, you have to put in 100 degrees centigrade worth of heat to get that water to boil off and let go of other water molecules. Hydrogen bonds are also responsible for another cool trick of water, surface tension. The reason why this water skittering bug is not sinking into that pond is because the water holding on to the other water molecules at the surface of that pond don't want to let go of one another. And in order to let this bug sink, those water molecules would have to let go of one another. This quivering drop, the same thing. This is a bag of water on the end of this branch, defying gravity. Everything we know about physics and biochemistry says that this drop should fall from that branch well before it reaches this size. But the water in that drop is holding on to the other water molecules in that drop, and they don't want to let go. And because water is holding on to water, that drop can quiver there and stay a drop and defy gravity. The gravity force pulling that water down isn't as strong as the hydrogen bond force holding the water to other water molecules in that droplet. So hydrogen bonds between water molecules stop things from slipping in between them because they're holding hands, and keep water stuck to water so that drops can form. So in this first section, we talked about water being a polar molecule. Water is polar because oxygen is electronegative. Oxygen exerts a strong attractive force for electrons in covalent bonds, and that strong attractive force makes that oxygen partially negative. The hydrogens of those covalent bonds are electron depleted, and so they are partially positive. This polar nature of water allows hydrogen bonds to form. The partially positive hydrogen of one water molecule interacts favorably, electrostatically, with the partially negative oxygen of another water molecule. That gives us hydrogen bonds. This is enormously important for water to remain liquid at room temperature, so that it can be a universal solvent. Hydrogen bonds also play a role in holding DNA together and allowing proteins to fold properly. So that's it for this first chunk. You can take a break now, of course. This is a good place to stop. But if you want to continue on with the rest of the lecture series for this first unit, you can do that as well. Thanks for watching.